What's up? I'm Flavor Flav, aka Flavor Flav, aka F Flav, and I'm head of Team BJ for ENEL 400, third year project. I'd like to thank Jaden Dang, Alfred Trong, Brandon Laley, Raw Kazoo, Catherine, and Arslan for all being fire team members. All you deserve the world. You should all have one of these Lambos. This team's mission was to create a device. We had an idea to create a device. And this device was going to fix a big problem that we noticed in the world. And we noticed that blackjack dealers were getting inefficiently trained at casinos. And that there was a need for a self-sustained, perfect blackjack player to train and create strong and efficient blackjack dealers to maximize casino earnings. So therefore, we as a team filled that gap with what we like to call the machine that will give you BJ. Blackjack, of course. BJ Machine. That's also one of my nicknames. Flavor Flav out. Demo coming.
Yeah. Now pan to the screen or just wait?
I might pause it.
Go.
I'm just gonna get careful and walk some water first, though. He's on his leash, so don't worry.
Now pan to the screen.
Yeah.
Okay.
Go ahead. There you go. Stop.
Hi everyone, welcome to the presentation portion of our final video. So, kind of just in summation, our full design was an automated blackjack player that obviously played cards for you. So, our prototype description, as you can see, we have our block diagram here. We first start with the table environment where we lay the cards, chips, everything like that. The camera then intakes the images off the table and reads the cards and the suit, and then identifies what hand we have along with the corresponding action. So we then use the Pi for our decision making and our card recognition, and the ESP32 is our servo control. So as you can see, our robotic arm is kind of the last portion. So everything is very interconnected. They all rely on their previous steps. So our physical implementation. So our final arm, as you saw in the video, was this green and white We obviously had big CADing for that arm, and then we had some servo wiring and the overhead camera mount that ended up being on the right side. So our prototype description. So the software loop that me and Jaden built, mostly Kanye, he was the brains behind this, was to first capture the images of the physical playing area, then detect what cards are on the table, make our decision using blackjack basic strategy, and then for our action is sent into the servos and our hit or stand is motion. So our testing. So we went through a lot of different testing, especially with the camera and the card recognition software. It very heavily relies on seeing the corners of the cards. So ensuring that we were in those boxes like seen on the screen here, where we could read the cards and then accurately understand what hand we have and then accurately do the associated motion. And then we just obviously did a lot of testing with the actual arm itself, the way the servos rotate, the way they stiff, the way they sit, everything like that is very important for just the structural integrity of the arm. We also have power stability and different logic and different servo supplies. So we are going to be using a different battery for the servos so we don't fry our normal fry. So how we met our design requirements. So we needed accurate table sensing. Kind of one of our criteria was we need to accurately get the cards and have it be a live system. And yes, we did that very effectively. I'd say we passed this test. Rule perfect decisions. Now, as far as basic strategy goes, we are perfect as it is just a hard coded set of decisions, but card detection is sometimes difficult as lighting and shadows play a very big role in the way the camera sees the cards. And so, yes, we can output a clear blackjack action. We understand it from our hand motion, but we do have a slight little bit of hiccup with the camera. We have smooth, so we needed smooth physical signaling, and BSP32 handles our PWM signals for the servo, and the Pi handles our vision logic. So yeah, everything is nice and smooth. I'd say we check that off. Stable integrated operation. The logic and the servo power are separate. So we have robustness, we have kind of failure protection. So yes, I believe we passed that outcome goal. So our schedule and our execution. So it obviously is a very big timeline that is, a whole semester's long, but we heavily kind of overlapped everything and we ended up with a lot of hours. I'm sure it's coming up here, but yeah, it's everything is very overlapped. Everyone was working with everyone throughout the entire process, and then all the hours were then logged. So the spending, what we originally had it for was $456. We ended up coming in under budget at $394. We also had some costs associated with the PCB. It was very kind of base level costs, so fabrication fee and shipping. And so the big deviations we came away from our plan was we went away from the Pi Camera V2 and then used a Logitech camera. A single controller concept changed to a Pi and the ESP32, and that is for easier motion control, more robustness, kind of failure, backups, everything like that. And yeah, isolated logic, like I just said. So, kind of what did our group learn? So, in engineering design, a focused task specific robot was better than copying a humanoid system. So there's no need to copy a system that we can already perform ourselves. That we cannot make a robot at this level that is a person. So We want clear subsystem boundaries, and this made the design easier to integrate. And then if we ever ran into issues, we could section out our design, find out where we're going wrong. And I think that's going forward and into fourth or fifth year, whatever, is that's a very big step, I think. Some prototyping, we ensure we test because early on in this project, everything kind of fell apart with that end and nothing worked. We found out. So, we can plan on paper as much as we need, but um, we're not always going to match that perfectly. So it's important to, start your prototype, encounter those hard road bumps, those issues, and then work through them. And then actual packaging, our wiring, our access to all the wiring, the ability to repeat our control, our motion, um, and these things all dictate whether we have an effective and reliable prototype. And then teamwork. We need to be extremely communicated between the mechanical and software guys. Hardware and software were probably the most interlinked. It was pretty much the same brain. And Alfie, me, and Jaden were all very um, focused in and collaborative on that portion. So I think maybe we needed more from other groups, but that's a key role and a big lesson that we learned kind of moving forward. And then you have to have effective planning. We had an absolute amazing team leader, and so she did very effective planning, very effective timelines, and for kind of the whole rest of the group, and maybe even her, we learned the vitality of a good and precise plan. And then so maybe some future improvements. So we need to refine the end effector for better chip handling. Basically, the chip dispenser kind of came out kind of rough because the chip is not very intuitive. It's weird to do, and we want to play more games in blackjack with this arm. And then so maybe we can move towards some kind of AI or like learning model that will then learn games or adapt. And again, just continue working on packaging, sensing, and gesture clarity. I feel they're all very defined now, but they can be much better. Everything can be better. And that's it. Thank you for watching.